So we've learned most of what we need to know in order to build up our adder in Logisim. There's only one other little section, which is a truth table, which we'll go through at the beginning of this video. And with that information, we'll be ready to go. So you'll note if you go into the resources section, you're going to find two files there. One of them is going to be an Excel spreadsheet. So you can go ahead and open that up just now, and you'll see it's simply the adder and subtractor. So if we get into the add subtract, you'll have seen this file before. Now the other file in the resources section is a Logisim file, and it's going to have the circuit build for our adder. Now I had thought about building this up live in the videos, but having attempted it previously, it just takes far too long and you're not going to get all of the value out of it. So what I've decided to do is actually to build up the working model, and what we'll do now in this video is talk our way through it. But first of all, let's go and we'll have a look at the Excel spreadsheet and we'll work out our little missing truth table. So let's use our old friends number 7 and number 5. And we can close this, so don't clear it, just press the close because we want to look at the data behind. So if we close that there, now what we're going to do is talk through the possibilities that we can have here, and what I might do is I'll make it just a little bit bigger so we can see it a bit better. Okay, so we have our 7 and our 5. Now we know that 7 and 5 are both normal numbers. So that means that whenever we add in the 24th bit, and we add the 24th bit in lines 8 and 9, then that 24th bit is going to be a value of 1 and 1. So there's always going to be a 1 in this column here and this column here. So in effect, this column is our 24th bit. And if the addition ripples another 1 into this column here, we can call this column our 25th bit. So as we mentioned in a previous video, this isn't an actual part of the IEEE. I've just added this in order to make the description a little bit easier to understand. So with this example here, we have our 7 plus 5, so we're always going to have a 1 here and a 1 here. Now the 7 and the 5 are going to be in the same exponent range, and we can see that down here. We've got our value for our EX is 2 and EY is 2, so whenever we subtract those off, the difference is going to be 0. So it means that whenever we go through and add these together, now you'll note there's not any shift here because EX is equal to EY. So when we add these two together, we're always going to have a 1 and a 1. So the two options that we're going to be left with is either we add another 1 in from here into this column, in which case we would have a 1 plus a 1 plus a 1, or we don't add a 1 in from this column here, so we don't shuffle any extra 1 in from the addition of the mantissa, in which case we're just going to have a 1 plus 1. Now you can see here in this instance that what's happened is we've got a 1 plus a 1 here, and that gives us a 0 and we carry the 1, and you'll have a 1 plus a 1, again that would give you a 0 and carry the 1. So we would have a 1 plus a 1 plus a 1 in this column. So that's going to give us 1, and we're going to carry 1 through. So that means that we're going to have this 1 rippling through the exponent. So the exponent increases by a value of 1. And if the exponent increases by a value of 1, then the mantissa will going to have to decrease by a value of 1. So that is, we're going to have to do this normalization. So that's one example here. So let's have a look and see what would happen with a slightly different example. Let's say we took our steady 7 plus 5, we could put say 70 plus 5, and that would mean that we've actually got an exponent difference. So you can see here the exponent difference is going to be a value of 4, so there is going to be some normalization in this case here. So if we were to look at this example here, then we're going to have our value of 1 and 1 because both are normal numbers. But in this instance here, the value of our y is less than the value of our x. So it means that we're going to have to shift the value of y so that the exponents are the same. So what we're going to do is we're going to take the value 1, 0, 1. In this instance here, it's going to be shifted to the right by this value here, which is our exponent difference. So that 1, 0, 1 is going to head off to 0, 0, 0, 0, and it will be 1, 0, 1. So it's shifted 4 places to the right. So it means here in this instance that we're going to, in this case here, have a 0 there and a 1 there. And again, we're left with the two possibilities. Either we carry a 0 in from here, in which case that just remains as a 1, or we carry a 1 in from here, in which case we would have a 1 and a 1, and when we add those together, that would go to a value of 0, and we would carry a 1 through to the next value here. So you can see here in this particular example we've ended up with a 0 and a 0. So when we add these two together, again we're just left with a 0 and 1. So there's no carry through, there's no ripple, and there's no normalization required. So what we're going to do is we'll go and draw out a little truth table of these bits. So we're interested in bits 24 and bits 25. So let's look at that truth table now. This is the truth table here. We have 3 inputs, SZ, bit 25 and bit 24. We have 2 outputs, the exponent and the mantissa. And I've added an extra column in here just for description. SZ tells us whether we're going to add or subtract. So if SZ is a 0, we're going to add. If SZ is a 1, we're going to subtract. So in this case, we're doing only the addition. So it means that SZ always remains at 0. So in effect, this column can be ignored because it doesn't change. We're always going to begin going through an addition. Now, the column 25 tells us whether we ripple 1 through onto the exponent. So that is if the value for column 25 is a 0, it means that the summation of the two values has resulted in us remaining within the same exponent range. So it means that the value for the exponent doesn't go up. And if the value for the exponent doesn't go up, it means that the result for the exponent is just the value EX. And it also means that we don't have to do any normalization. So it means that the mantissa is the value for our MR. Now that's the case when bit 25 is a 0. Now when bit 25 is a 1, it means that the addition has ensured that we actually go up by a factor of 1. That is, we have moved from one exponent range into the next exponent range up. So it means that the output for the exponent is going to be the value of EX plus 1. So we've gone up that extra exponent range. So that means we're going to have to do the normalization. So it means that the mantissa is going to have to be divided by 2. So bit 25 here really controls whether we stay in the same exponent range or we go up 1 in the exponent range. And it doesn't matter what happens in that case on bit 24. Bit 24 here could be a 0 or a 1. And in this case here, it can be a 0 and a 1. So the one issue here that we have to deal with is the fact that for the option bit 25 0 and bit 24 is a 0, that actually never ever occurs. And you can convince yourself of that by putting some values in and testing it for yourself. So it means that in this case here, we can put a big cross in here because that is a don't care condition. And if you notice this one here, there's no change, so we'll call that NC for no change. And this one here, the 1 gets added on to the exponent, so we'll ripple the 1 through. So I've put that as an R, so that's R for ripple. And this one here is an R for ripple. Now, if this is a don't care state, it means we get to choose, and we can choose to call it whatever we want. So in this condition, this option here, we'll just call that no change. So it means that this truth table, all that happens is bit 25 determines whether we just have the exponent out. So if the exponent EX comes out, then the value for MR also comes out at the same time. If bit 25 is a 1, then the value for the exponent is EX plus 1. In that case, the value for MR is MR divided by 2. So we have to follow just this truth table here, and bit 25 will determine whether we keep EX the same or whether we change the value for EX, and also whether we keep MR the same or whether we change the value for MR. So let's open up the Logisim file again. Now if you make sure you're on the top level here, you see that what we want to do is we want to add an input into here for X and also from Y, and also the add subtract button. And we want the output to be the X plus Y. So if we head in here, you'll see that we've created the inputs here. So this is the input for Y, input for X. So I'll quickly show you these just so you can get started if you're building it yourself. You can click on the input. We want to change that to a 32-bit input, and we'll face it east, and we're going to call that input X. So what we'll do is we'll put a tunnel. So here's your tunnel here, and we'll call that X, and we're facing it west, and we're going to make that a 32-bit tunnel, and we connect that onto here. And now I've added a probe in the ones up here just so we can see it in hexadecimal as well. So there's your probe, and we'll face it east and make sure that the output is hexadecimal. We'll connect that up, and that's us created that X input. Now to create the Y input, you just Control C, Control V, and that's us now created a Y input. If we change this here to a Y, the label. Okay, so it means that you can quite quickly build up these little structures. Now, as I said, I'm not going to build all of them because it just takes far too long. It takes long enough to talk my way through exactly how it works. So if I went to build them live here, the videos would just take hours and hours. So we're interested in getting into the splitter. So the splitter is going to split the signal X and Y into the sine exponent and mantissa for X, sine exponent and mantissa for Y. So let's drop down inside, and you can see here that we're going to have the inputs, which are our X inputs and our Y inputs. Now note, I've just put the tunnel and butted the tunnel up against that there. That's why it looks like that. Okay, and we're going to have the outputs. So we're going to have the outputs, which are the sine exponent mantissa for X, sine exponent mantissa for Y. And all we've done is we've taken the X input, which is this input here, and we've put it through something called the splitter. And the splitter has brought out the mantissa, the exponent and the sine for each of these. And you'll get the splitter in here. So there's a splitter there. And you'll note if you click on it, you'll see the splitter has got 32 bits. So it's a 32-bit splitter. That is the input is 32 bits. But then that 32 bits fans out into 3 prongs. So the 3 prongs here are going to be one for the mantissa, one for the exponent, and one for the sine. So in this instance here, I would change that thing there to 3 prongs. So there's 1 in, 3 out, and it's going to be 32 bits that come in. And I can then change the values here, and you can change the values so they're the same as the values you have in this one here. So it means that first lot here 0 to 22, so that's the first 23 bits of the mantissa. The next prong here is going to be the middle one, is going to be the 8 for the exponent, and the last one is going to be the 31st bit, which is the sign. Okay, so that's how we split these things up. It's pretty straightforward. So if you like, we can think about the splitter as modelling the lines 2 and 3 here. So in lines 2 and 3, we split the y value into sine, exponent, mantissa, and we split the x value into sine, exponent, and mantissa. Now the next section is going to be the swap section. So if the value for ex is greater than or equal to ey, we don't need to do any swapping. But if the value for ex is less than ey, then we're going to have to swap them round about. So the ex becomes ey, and ey becomes the ex. So let's have a little look at that here. So this is the component here, exponent, difference, and swap. So we're taking the sine, exponent, mantissa for x, and we're taking the sine, exponent, mantissa for y, and we're putting them into this box here. So I've called that exponent, difference, slash swap, so that's this one here. So let's just head in and we'll look and see how we're going to build this. So we're going to have the inputs. So we're going to have the x input for the sine, y input for the sine, and we're going to have the x input for the exponent and the y input for the exponent, and the same for the x for the mantissa and y for the mantissa. Now what we want to be able to do is we want to see whether we have to swap the values for x and y. So we can take our x and we can take our y and we can put it through a subtractor. So you get the subtractor down here, so we go to arithmetic and you'll see the subtractor here. So whenever we subtract these off, this is going to be xe minus ye on this line. Now, if the value ends up being negative, then it means that the value for xe will be less than the value for ye. And that means that we're going to get this line here going high. So when this line here goes high, this tells us that we're going to have to swap these two round about, because we know that we want to keep the x greater than y, but if this goes high, it means that the value is negative, so it means that in effect y would have to have been greater than x. Well, if you want, you can just put a couple of values in. You could take your copy of this here and a copy of these, and you could test this out for yourself. So you could just put some values in to the input here for x and the value for input into y, and you can simply run through the simulation. Okay, and you can put values in and you'll see that depending on whether x or y is greater or less, you'll get this line here going high or low. Okay, so I suggest you do that as well, just to convince yourself of these circuits and how they're working. So it means that if this line here goes high, we've actually had to produce a swap. Now we'll also go through the option here, and this is going to be ye minus xe. So we're going to take the ye here to the top line, and the xe here will go now to the bottom line. So we just in effect swap these two lines round about. So we're producing these two options here. And if the value here goes high, that is we have to swap them, then if that's the case, the difference here that we put out is going to be, that'll be of 1, so it means that this is a value of 1 here, so it's chosen the bottom line, so it means that it will be choosing YE minus XE as the exponent difference. And if there wasn't a swap, then it means that we're going to have this line low. That means it chooses the top line, so it's going to choose XE minus YE. So that's working out the difference, and it works out the value for XE minus YE, depending on whether we have to swap them or not. Now, the reason why we put this little swap tunnel here is that we need to be able to now swap the values for the sine, the exponent, and the mantissa. So we do that down here in this little swap part. So each of these is just really the same with just different inputs, so we really need to only talk through one of them. So for example, we could talk through this exponent swap. We can put the XE in and we can put the YE in. Now, if the swap is low, it means it just passes the value 0, which is the XE. So XE just gets passed to the output, so there's no swap. And the same for this one here for the sine, and the same for this one here for the mantissa. But if the swap was to go high, that would mean that the value for the X here would actually get passed through the value of Y. So this YE would then become the X value. And the same here for the mantissa, the Y would then become the X. And the same for the sine, the Y would become the X. Of course, if we've had to swap it, we'll also have to make the X value equal to the Y value. So down below, if we have to swap, then the Y value, the X value, will be passed through to the Y, the X will be passed through to the Y, and the X here will be passed through to the Y. If there's no swap, then we just pass through the value of Y gets passed through, and the value of Y here gets passed through, and the value of Y here. So this is just how we're going to swap these over. Now, if you like, as I say, just go ahead and put some values in and test this for yourself, and you'll see the swap happening. So that's the video going on now for 20 minutes. We've still got a bit to go through in order to finish. So what I think we'll do is we'll finish this video here, and in the next video we'll start exactly where we left off, and we'll get through the rest of the adder in the next video. So thank you for listening. I'll get you on the next video. Goodbye.